Good evening, and welcome to the Scientific Adventures of Beardman. Well, today we're going to look at the connection between work and energy. It's commonly called the work-energy theorem. And it's actually very similar to a concept we've already considered. And that is that an impulse causes a change in momentum. Or Newton's second law of force causes an acceleration. Okay, so the root of it is, of course, Newton's second law that a force pushing something causes it to change its velocity. Okay, well, how much does it cause it to change its velocity? You can use F equals ma. If you want to look at it, sometimes it's helpful to look at it in terms of impulse. We saw that last unit. A force acting for a certain amount of time changes the momentum of the object. Okay. In this case, a force pushing for a certain amount of distance, so we're talking about the distance that object gets pushed, will cause a change in the energy of the object. Now, it can do this in a couple ways. It can, the force acting over the distance can cause the object to accelerate, or a force acting over a distance could give an object potential energy. Okay, and so that's the basis of the work-energy theorem. Is that work is essentially our force, the way we're looking at the force, and how long that force is acting. In this case, how long in terms of a distance, and that gives an object energy. So work is very accurately thought of as a transfer of energy. Okay, the thing doing the work is losing the energy, and the thing having the work done on it is gaining the energy. Okay, and so there's a transfer of energy taking place there. Okay, now for a lot of the stuff we're going to look at this unit, I eat my food, I get energy, and that chemical energy allows my muscles to extend and push an object to give it kinetic energy. Okay. Now, a couple things. First of all, we haven't yet talked about direction. Is work, is energy, are all these things vectors or are they scalars? Well, it turns out they're scalars. There is no direction associated with work, even though the force, and the distance have to be in the same direction. The work ends up, well, we'll just say it cancels out the direction, okay, and leaves it as a scalar. Okay. Can we have a negative work? Sure, if the work is being done by the object, we can consider that as being negative because it's losing energy, it's giving its energy to something else. If we consider it positive, the work is being done on the object. That means something else is giving energy to the object. So we could look at that as a positive work being done. The other thing that we have to consider is going back to Newton's second law. Remember, it's not just any old force that we can plug into F equals ma to figure out the acceleration of an object. It has to be the net force, right? Because we have an object, a force pushing this way and a force pushing this way with the same strength. This force isn't causing an acceleration. By itself, it would have caused a certain acceleration, and by itself, this would have caused a certain acceleration. And so when we take a look at the work-energy theorem, we have to be very careful that the work that we're looking at is the work done by the net force on the object. Okay? And that would give us the kinetic energy of the object in the end. Now, we don't necessarily have to look at it that way. I could push a sofa across the floor, and that force of pushing the sofa I could use over the distance I push, and that is how much energy I transferred to the sofa. But anytime you push a sofa, there's going to be friction. Okay, and that would be the sofa transferring energy to the floor. It's really becoming thermal energy, okay, which we'll get to in another unit. Okay, so if I'm pushing on, we can use my force to force times the distance I push, and that's how much energy I transfer to the sofa. It just won't be the kinetic energy of the sofa if the sofa is in the same time transferring energy to the ground or to the molecules in its feet and in the ground. So if we want to calculate the kinetic energy of the sofa, we'd have to be using the final kinetic energy of the sofa, we'd have to be using the net force. Okay, then we would know how much energy has been transferred into the sofa and is still there, and therefore how much kinetic energy the sofa now has. Of course, once we know the kinetic energy, then we can go through and calculate how fast the sofa must be moving in order to have that much kinetic energy. Okay, and that's it. That is the work energy theorem. Basic idea: work is the force part of it. It's the transfer of energy from one thing to another. Energy is what's gained by the object or transferred to the object. Okay, so work is the process. The energy transfer is the result. All right, we'll see you next time on the Scientific Adventures of Beardman.